Dark matter is one of the most perplexing and fascinating mysteries in modern astrophysics. Despite its elusive nature, the evidence for dark matter's existence is overwhelming. Yet it remains deeply frustrating because we still don't fully understand what it is. Dark matter is inferred from its gravitational effects on visible matter, radiation, and the large-scale structure of the universe. Yet it has stubbornly resisted all attempts to be directly detected or explained by current theories. We do know a few key things about dark matter. It's believed to be cold, meaning it moves slowly compared to the speed of light. It's also collisionless, meaning it doesn't interact with itself or ordinary matter in any significant way beyond gravity. Most intriguingly, dark matter is incredibly abundant, so much so that it's thought to make up about 85% of the total mass of the universe. Understanding what dark matter is made of could provide crucial insights into the dynamics of galaxies and the evolution of the universe as a whole. Given that it's the most common type of particle in the universe, figuring out its nature is one of the most pressing questions in physics today. To grasp the challenge of understanding dark matter, imagine being in a small boat in the middle of the ocean on a dark night. In the distance, you see the faint lights of a shore. These lights tell you that the shore exists, but they don't reveal anything about what that shore is like, whether it's rocky, mountainous, or covered in dense jungle. This is similar to our current understanding of dark matter. The luminous objects we observe in the universe, such as stars and galaxies, give us clues that dark matter is there. However, just as those distant lights don't tell you about the shore, the visible matter in the universe doesn't tell us what dark matter's made of. We know it's out there, influencing everything we see, but its true nature remains hidden. The evidence for dark matter comes from various astronomical observations that cannot be explained by visible matter alone. One of the most compelling pieces of evidence is found in the rotation curves of galaxies. When we observe how stars move within galaxies, their speeds do not decrease as expected with distance from the galactic center. Instead, they remain relatively constant, suggesting the presence of additional unseen mass, dark matter, exerting gravitational force. Other evidence comes from the temperatures of galaxy clusters. These massive structures are too hot to be held together by the gravity of their visible matter alone. Dark matter provides the additional gravitational pull needed to explain their stability. Gravitational lensing, where light from distant objects is bent around massive structures, also reveals dark matter's presence. The bending is stronger than it would be if only visible matter were involved, indicating more mass. Again, dark matter. The large-scale structure of the universe itself, which shows how galaxies are distributed across vast cosmic distances, matches predictions made when dark matter is included in models. Finally, the cosmic microwave background contains patterns that suggest dark matter played a crucial role in the early universe. Together, these pieces of evidence make a compelling case for the existence of dark matter, even though its exact nature is still unknown. While we have strong evidence that dark matter exists, we also know quite a bit about what it isn't. It's not made up of the same kind of matter that makes up stars, planets, or any of the other objects we can see in the universe. These familiar forms of matter are simply not abundant enough to account for all the gravitational effects observed. Nor is dark matter made up of objects like black holes, rocks, or dim stars. Such things would still interact with light in some way, and dark matter does not. For dark matter to explain the observed phenomena, it must be cold, meaning it moves at relatively slow speeds compared to the speed of light. This is crucial because fast-moving particles would not clump together to form the dense structures we see in the universe. Additionally, dark matter must be collisionless, meaning it doesn't interact with itself or other matter through forces like electromagnetism, which is why we don't see it directly. It only interacts through gravity, which is why it's detectable through its influence on visible matter. One of the strongest pieces of evidence for dark matter comes from studying the rotation curves of galaxies. In a galaxy, stars orbit around the center due to gravity. According to Newtonian mechanics, we expect stars closer to the center of the galaxy, where most of the mass is concentrated, to orbit faster. As we move farther out, where there's less visible mass, the orbital speed of the stars should decrease. This would produce a rotation curve that rises steeply near the center and then falls off. However, observations tell a different story. Instead of slowing down, the orbital speed of stars levels off and remains constant, even far from the galactic center. This discrepancy suggests that there's much more mass present than what we can see, an invisible mass that extends far beyond the visible boundaries of the galaxy. This unseen mass is what we refer to as dark matter, and it appears to be spread out in a halo around galaxies, affecting the motion of stars and gas. Further studies have shown that this dark matter isn't just randomly distributed. It forms halos around galaxies with a specific structure. This structure is described by what is known as the Navarro-Frank-White (NFW) profile, named after the astronomers who developed it. The NFW profile gives us a formula that describes how the density of dark matter changes with distance from the center of a galaxy. According to the NFW profile, the density of dark matter is highest at the center of the galaxy and decreases with distance, following a specific mathematical pattern. This profile fits observations of many galaxies and galaxy clusters, suggesting that dark matter behaves in a similar way across the universe. This consistency provides insights into the formation and evolution of galaxies and their dark matter halos. While theoretical models provide a framework for what dark matter might be, finding concrete evidence of its existence requires innovative experimental approaches. Various hypotheses suggest that dark matter could be made of several different types of particles, each with unique properties and detection challenges. One prominent candidate for dark matter is weakly interacting massive particles, WIMPs. These hypothetical particles would interact only very weakly with ordinary matter, making them hard to detect. Scientists have designed numerous experiments to catch WIMPs in the act, including using ultra-cold detectors and sensitive instruments buried deep underground to shield against other types of radiation. Another intriguing candidate is axions, which are very light hypothetical particles predicted by some theories to solve certain problems in particle physics. Axions might interact very weakly with ordinary matter, but they could be detected through their effects on electromagnetic fields or by their potential to convert into photons in strong magnetic fields. Primordial black holes are another possible form of dark matter. These are black holes that could have formed soon after the Big Bang, and their presence would have significant effects on the formation of structures in the early universe. Detecting primordial black holes would involve looking for their gravitational effects or radiation they might emit. Sterile neutrinos are a type of neutrino that doesn't interact via the weak force like regular neutrinos, but could still be part of the dark matter. They're difficult to detect because they interact even less with matter than ordinary neutrinos. To identify these dark matter candidates, scientists use a variety of experimental techniques. One method is gamma ray detection. If dark matter particles can annihilate each other, they might produce gamma rays that can be detected by space-based telescopes. Another approach involves observing the effects on stars and planets. Dark matter particles might cause unusual heating in stars or other celestial objects if they interact in specific ways. Ultra-cold detectors are designed to pick up tiny amounts of heat generated when dark matter particles collide with the detector material. These detectors are often located deep underground to minimize interference from cosmic rays and other sources of noise. Pure xenon or argon detectors are another method where these noble gases are used in highly purified and low background environments. The idea is that dark matter particles might interact with these gases and produce detectable signals, such as flashes of light or tiny electrical charges. Despite these extensive efforts, direct detection of dark matter has so far been elusive. However, the ongoing search is crucial because even negative results help refine theoretical models and focus future experiments. Confirming dark matter's existence is already a significant achievement, though the nature of this dark matter remains unclear. Neutrinos are an example of dark matter particles in the sense that they do not interact with light, but they are not massive enough to account for the total amount of dark matter we observe. Thus, researchers continue to explore different types of particles, such as heavy neutrinos or other exotic particles like WIMPs, to find a better match for the dark matter we know exists. Additionally, understanding dark matter might also shed light on the conditions of the early universe. It's possible that dark matter played a role in events such as baryogenesis, which explains why the universe is dominated by matter rather than antimatter. Investigating these possibilities helps scientists connect dark matter research with broader questions in cosmology and particle physics. Dark matter remains one of the biggest puzzles in science today, posing more questions than answers. Whether dark matter is a single, simple type of particle or a more complex mix of different particles is still an open question. The possibility of new forces or undiscovered theories of gravity also lingers as potential explanations. As it stands, dark matter serves as a framework for understanding many cosmic phenomena, providing a foundation even though the details are still being worked out. The current state of knowledge about dark matter is similar to an unfinished house that's structurally sound but lacking in the final details that would make it complete. Could dark matter provide clues to other cosmic mysteries, such as the nature of gravity or the origins of the universe? Let us know in the comments below. And if you want to know more about the mysteries of space, don't forget to watch our video on wormholes, the key to interstellar travel. See you in the next one. Bye.